We're going to accomplish a couple things with this example. So first off, we're going to tilt our camera a little bit. There we go. And second, we're going to talk about small k ice table problems. And what you can do is, if k is small enough, you may assume that you can ignore x, then check the assumption. And in general, if k, whether it's kc, kp, or some other k that you might see, if it is less than 0.0001, 10 to the minus fourth, then you may ignore x. Because k is small enough, the reaction, which means that the reaction doesn't go very far at all, and you may ignore x, and I'll show you what that means. And we're going to specifically do an example where k is a little larger, because sometimes when k is a little larger, you can still ignore x, then check the assumption. And the assumption that you need is that x, the amount of reaction, must be less than 5% of the initial concentration. And so here the initial concentrations are 0.01 and 0.02. And so when we find what x is, it's called the amount of reaction. It's also called the extent of reaction, how much reaction actually occurs. As you saw in the last ice table, x is something that is part of the change in concentration. Let me see, do I have 2 pages? Oh, good, I have 2 pages for this one, because this is potentially a long one. All right, so we set up our ice table. Our concentrations here are in molarities. Maybe we should call this a mice table. And filling this in, so we have N2 is 0.010, H2 0.020, and again, no information about our product. Assume it's 0, and that's a good assumption. Now, the reaction has to go in the forward direction to create some products, because our QC would be 0 if we calculate it, and the reaction must always go towards the 0, because there can't be less than 0. Anyway, this reaction based on our Kc value is not going to go very far, but it will go towards the products. So we take a minus x there. This one's going to be minus 3x, because the coefficient always shows up in the minus part, because it takes 3 times as much hydrogen to react away as the amount of nitrogen. Then it must be plus 2x on the product side, because we're making products, and there's that 2. Those 2's show up for a reason together. So then we get our equilibrium values in terms of x's. And we write them all out, and then we can plug them into our Kc expression. So Kc is products raised to coefficients, and so that 2 shows up 2 different places now. And the 3 shows up 2 different places as well. So please be careful about that. It's an easy mistake to make, and it changes the math entirely. All right, so plugging in values now for our equilibrium, we see that we have 2x is our concentration at equilibrium. that gets squared. N2, 0.010 minus x, and that's just raised to the first power. Then hydrogen, 0.020 minus 3x, and that gets cubed. And we have a fourth power here. And I don't know about you, but my ability to solve fourth order polynomials is very limited. I'm sure it can be done, but when you get anything more than second power, so second power we can and will use the quadratic. Third power, well, we can solve real gas equations for that iteratively, so we do know how to solve that. Fourth power, nope. So that's your clue that there must be a simplification here to solve this problem, in fact. And so what we're going to do is we're going to assume k is small, which means that you can ignore x. And in fact, we're going to assume that we can ignore 3x. And so what that means functionally is, in the denominator here, instead of 0.010 minus x, we're going to cancel out the minus x. And we're going to cancel out the minus 3x. And when we rewrite this on the next page, it will be actually with the kc value. So 1.1 times 10 to the minus third equals 2x squared over 0.010, 0.020 cubed. So we've just totally gotten rid of those x's. We assumed, we ignored them. And then we will have to check at the end, and it will be true for this example, that x must be less than 5% of the initial concentration, and in fact, 3x will be less than 5% of the initial concentration here. All right. Now, we still have a second order, but we've just gotten rid of our quadratic equation because our x squared term will be equal to just a number. So let's see, in this denominator here, I have, well, let's multiply all these terms times this number over here. We get 1.1 exponent third minus times 0.01 times 0.02 times 0.02 squared. I get 8.8 times 10 to the minus 11. Equals 4x squared. Please be sure to always square the 2 number too. And then we'll divide both sides by 4. 2.2 times 10 to the minus 11 equals x squared. And x equals the square root of that. Shift square root. 4.7 times 10 to the minus 6. And we've got just 2 sig figs throughout this problem, so we will keep 2. Though if you keep 3, 3 is always fine. That is a molarity. And now we can come back to our molarity ice table and put in a second line. And so now here's the tricky part too. We solved for x. X equals 4.7 times 10 to the minus 6. However, the concentration of NH3 equals 2x. So we will multiply that 4.7 exponent 6 minus times 2. We get 9.4 times 10 to the minus 6 molarity. And that's what we're going to put up here. So 9.4 times 10 to the minus 6. Let's check. We'll subtract off 3x from the 0.020. And let's just figure this out. So 0.02 minus 3 times 4.7 exponent 6 minus. I get 0.01998, which to 2 sig figs, well, let's see, so concentration of H2 0.01999859, which no matter how you do it, if you round it to 2, 3, or 4 sig figs, ends up being 0.020. So our assumption that K was small shows that we have really no change, no measurable change since it's 2 sig figs in that concentration. Since this is the toughest test for the 5% test, we'll take the 3 times x divided by our initial concentration, 3 times 4.7 exponent 6 minus. We'll divide it by our 0.02, and we'll multiply that times 100. Then we get that 3x is 0.07% of 0.020 molarity, and it has to be less than 5%, so it is well less than that. Anyway, when you do the subtraction here, you'll find that you are subtracting an inconsequential amount as well. And our equilibrium concentrations, it doesn't always work out like this. Sometimes you will see a small decrease, but in this particular problem, we ignored the x and the 3x, and we saw that the initial concentrations essentially didn't change. And to summarize, you may always do this when K is less than 1/10,000th, always. If it's greater than that, you can make the assumption and then check it. And so this right here was our check. Okay. Let's see. Let's do another one. In this particular one, I got pens flying everywhere. This example is called the perfect square, and here we go. This time it says the value of Kc is 57, so Kc is definitely not small. We have our reaction. Determine the equilibrium concentrations if 1 mole of hydrogen is allowed to react with 1 mole of iodine in a 10-liter container. So 2 things happening here. We don't have our molarities. We have to calculate them. And there's something called the perfect square going on. And I think this might only give me 1 page. Oh, nope, we have another page for this too. So we will become nearly professionals at writing out ice table problems. We set it up. We put in our Kc value, 57.0. Now, our initial concentration of hydrogen is 1 mole per 10 liters, so 0.100. Same concentration for our iodine, and no information about our product. So our changes, we have 1 coefficient here, so it's just going to be minus x, and plus 2x for the 2 there. Then we write this out. And when we plug into our Kc expression, what we find, and I'm going to write out the whole process so you can see it all. And I'm going to take my time and put the products on top. Reactants on the bottom. And when I plug in, well, let's plug in our number, 57.0. I have 2x squared on top. I have 0.100 minus x squared for each of the reactants on the bottom. And this is what's called a perfect square. What I mean by that is both sides are squared, both the numerator and denominator are squared, so we can take the square root of the whole thing. Anything you do to one side, you do to the other side, so you square root the other side as well. I'm going to work up here. There is another page for this one though, and it says, so square root of 57, 7.55 equals, well, we just take the squareds away, 2x over 0.100 minus x. And now we have to just solve for x. We will be ignoring the negative roots here, and that's because the positive root is the one that we're going to look at. So even though this is plus or minus and plus or minus, we only have to look at the plus. And from there, so we multiply this across, we get 0.755 minus 7.55x equals 2x, which ends up being, take the 7.55, we get 9.55, x equals 0.755 minus 9.55. How about divide by, Bill? 0.755 divided by 9.55, 0.0791 molarity. And good, let's check. Good, it's less than our initial concentration. That's a good sign that the math works. And now I didn't really leave enough room for my equilibrium concentrations down there. So my equilibrium concentration of HI is 2 times this number, 0.0791 times 2, 0.158 molarity. And my concentration of H2, which will be equal to my concentration of I2, is 0.1 minus this number, 0.0791. 0.0209. And 2 or 3 sig figs would be fine there. And let's see, come back to our problem. It did ask us to determine the equilibrium concentrations, and we have done that. There was another page for you to work on it, and that's the end for this one.